Okay, so last time we started by discussing different forms of energy. We talked about kinetic energy and we derived gravitational potential energy. We're going to do an example, but before we get to the example, I want to make one important note about gravitational potential energy. And that is that, in general, we were going to assume that gravitational potential energy is zero for an object that is on Earth's surface or at the floor. Now, you might be saying, those two things are not the same thing. If I'm in my classroom, the floor is maybe a meter below me, but Earth's surface is like 3 or 4 meters below me. Those are not the same thing. You might even argue that, well, technically, if you're here in Sequoia, you're like 1,000 feet above sea level. Is Earth's surface like the level in Sequoia, or should we be using sea level, or what? The shorter answer is we don't really have to deal with it. It doesn't really matter as long as you're consistent. It's more of an issue in AP, but we won't worry about it too much for Regents. Just wherever the, I guess I would call local floor or ground is near you, that we're more than able to use that. So let's get to our example. Our example is going to have to do with a simple machine that we've invented over the years, the ramp. What is easier, lifting something straight up or using a ramp to push or pull it up? Let's say that you work for a moving company. You're trying to move a heavy object from the ground to the second story of a building. The object has a mass of 50 kilograms that you're trying to move. So what is going to be the pros of using a ramp? What is going to be the cost of using a ramp? And how do we put this in physics terms? First thing we might want to look at is what's the initial gravitational potential energy of the object? Well, all we do there is calculate the initial gravitational potential energy. Pretty straightforward. Gravitational potential energy is given by the equation mgh. I put the i's in because we're talking about initial. The mass of the object is 50 kilograms. The acceleration due to gravity is 9.81 meters per second squared. And the height of the object initially, while it's on the ground, so that's 0, and anything times 0 is 0. So we have the initial gravitational potential energy is 0 joules. In order to lift the object straight up to a height of 4 meters at a constant velocity, how much work must be done? We know the equation for work, and let's see, if you're lifting it, it's going to be the applied force that you're using to lift it. So the equation for work would be the applied force multiplied by the displacement times cosine of theta. The displacement is going to be 4 meters. You're pushing up on it. The object's being displaced upwards, so we can reasonably assume that theta in this case is 0, so cosine of theta is going to be 1. But we don't know how big the applied force has to be to lift this at a constant velocity. So at this point, this is where we need a free body diagram. Here's your object. If you're lifting that object, then your applied force on it is up. You're counteracting the force of gravity on it, which is down. You're lifting it in this direction, so that's D, so therefore D and FA are in the same direction, which is why we said that. And your axis would look like this, X, Y, plus. The net force equation would be F net Y equals FA minus FG equals MAY. You're lifting it at a constant velocity, so that term is 0. Therefore, FA equals mg, and you can replace it in your work equation. The work done by the applied force is equal to mgd, which is 50 kilograms times 9.81 meters per second squared times 4 meters. And it turns out that the work done by the applied force, in this case, is 1,962 joules. So, you did work, you transferred some energy. What's the new gravitational potential energy? If it seems like it's kind of a silly question, it is, because you already know it. The initial was 0, but then you did this much work, 1,962 joules. Where did that energy go? It went into increasing the gravitational potential energy because the object raised. As a matter of fact, if you look at this equation, mgd, d, the displacement, you're lifting it up. The displacement is just how much height you've given the object if it started at 0. So this is really the exact same thing. Okay, it's the exact same calculation, but I'll show it anyways. The new gravitational potential energy is 1,962 joules. So that's lifting it straight up. Easy. What if instead we used a ramp to lift it up? Does that decrease the amount of work? What is the whole point of using a ramp? Suppose instead the company decides to pull the object at a constant velocity up a frictionless ramp that's 10 meters long, reaches the same height of 4 meters. First of all, what's the angle between the ramp and the ground? A little bit of trig review. We've got a 10-meter long ramp that goes up a height of 4 meters. okay, we can figure out that angle that the ramp makes between it and the ground. We can do this because we know trig. Okay, think about SOHCAHTOA. This is the opposite side. This is the hypotenuse side. So means sine and opposite over hypotenuse. In this case, we have sine theta equals 4 meters over 10 meters, or sine theta equals 0.4. And remember, to find an angle, we have to take the inverse sine. So we do theta equals the inverse sine the negative first of 0.4. It's not really raising it to the negative first, but that's the notation we use. There's a button on your calculator that does that. 0.4 second sine tells us that the angle is 23.58 degrees. Okay? So again, remember, sine, cosine, and tangent, they're not scary. They're just ways of figuring out if you have a right triangle. There's different ways of figuring out angles or side lengths if you have enough other information. It's just a way to use the ratio of the side lengths and relating it back to the angle that must be being created. Now, with this ramp and that angle, how much work must be done in order to pull the object up the ramp? So again, we're talking about work. We're pulling it up, so let's say work done by the applied force equals Fa times the displacement times cosine of theta. So again, we don't know Fa, we don't know how big the force is, but we do know the displacement. This time it's going to be 10 meters, because we're not just lifting it up 4 meters, we're pulling it along the ramp surface. And the angle between the applied force, you're pulling it up, and the displacement is also up the ramp, again, should simplify down so it's cosine of 0, and you get 1. Remember, this theta is not the angle that the ramp makes. This angle is the angle between the applied force and the displacement. So once again, we have to find the applied force. It's a more complex free body diagram this time. Here's our object. On the ramp surface, there's going to be a normal force on it, perpendicular to the surface. That'll look like this. I should put in my axis right now. Okay, there's the normal force. There's the force of gravity. And someone is pulling it up the ramp. Now, the normal force is in the positive y direction, the applied force is in the positive x direction, Fg is in neither direction. It is kind of in the negative x direction, kind of in the negative y direction, so we need to split that into components. We need to label where theta is. Remember, theta goes between the perpendicular, between the force of gravity and the component that's perpendicular to the ramp surface. Ramp surface is on this plane. This is the component that's perpendicular, so theta goes here. And that means that this component must be Fg cosine theta, which means the other one is Fg sine theta. Remember, with ramps, sine and cosine switch. There's a whole bunch of math that goes into that. We can prove it. If you're a little rusty on that, feel free to go back and watch that video. The net force equations. In the x direction, which is going to be the most important one for us, Fa minus Fg sine theta equals max. It says that we're pulling the object at a constant velocity, so no acceleration. Therefore, the applied force must be equal to mg sine theta, since Fg is equal to mg. In the y direction, just for practice, we get Fn minus Fg cosine theta equals may. The object is also not accelerating down into the ramp or blasting up off of the ramp. So the acceleration in the y direction is also 0. Therefore, Fn equals mg cosine theta. Okay, little review with your free body diagrams and net force equations. But now we have a value for Fa, and you'll notice, since you know sine is always less than or equal to 1, the applied force, since we have an angle here, this is the angle that we just found up here. Okay, this angle is the ramp angle. So this sine of, I guess, 23.58 is going to make the applied force less than the force of gravity, less than just mg. You're taking mg and multiplying it by something that is less than 1, so it's going to reduce. The applied force is not as much. So notice that with a ramp, we are not pulling as hard to get the object up the ramp as opposed to up here, where the applied force had to be just mg. So the work done by the applied force equals mg sine theta times d. So that would be 50 kilograms, 9.81 meters per second squared. This angle, and I know it's confusing, this angle, this theta, was the ramp angle. So that's sine of 23.58 degrees times the displacement of 10 meters. We can solve for the work done. I'm going to do the angle first. 23.58 sine times 50 times 9.81 times 10. And within a little bit of a rounding error, look at that. It's the exact same amount of work done, 1,962 joules. So interestingly, the force went down, but the amount of work done stayed exactly the same. That's kind of weird. Something else must have changed. And if you think about it long enough, you'll get it. It's the displacement that changed. What happened here is that, and I'll explain this more in a little bit, basically a smaller force was used over a bigger distance, so the same amount of work was done. But let's find the gravitational potential energy at this height. Remember, gravitational potential energy is only based on the final height, or whatever height the object is at. Doesn't matter how it got there. So PEGF equals 50 kg times 9.81 meters per second squared times the final height of 4 meters. The final potential energy, as we expected, is 1,962 joules, because that's where the work went. That's where the energy was transferred into. So our conclusion here, the amount of work done to raise an object to a certain height does not depend on the path taken by the object. And I should note that we're assuming no friction here. This would actually be a different story if we were talking about friction. So assuming frictionless. No matter if we just lifted the object straight up or if we pulled it up a ramp, the amount of work done was the same. Okay? It only depended on the change in height of the object. And this, I know we're saying work done here, is similar to change in gravitational potential energy. The change in gravitational potential energy does not depend on the path the object takes. It just depends on what the initial and final heights are. What was the change in height? So again, the reason that it was the same amount of work done is even though the force was smaller, mg sine theta compared to just mg, the displacement of the object was bigger. Okay? Humans use ramps not because they reduce the amount of work that you have to do, but because humans are better at exerting smaller forces, like in the ramp case, over larger displacements. We're not built for exerting large forces over small displacements. So that's why humans use ramps. Okay? Now, let's get to one last part of this example. If that object up top were to suddenly fall from its height of 4 meters back to the ground, what would its speed be just before it hits the ground? Here's the ground. Here's the object right before it hits the ground, and it falls from up here. Initially, what type of energy does the object have? Okay, it falls from up there. So it's got gravitational potential energy. Why? If you're thinking because it's not moving yet, that's not really the reason. Objects can be on the ground and not moving and still not have any gravitational potential energy. It's got that gravitational potential energy because it is up above a surface. It is above some height above the floor. Okay? So initially it's got gravitational potential energy. At the end, as it falls, because the height is decreasing, it's going to lose that gravitational potential energy. But what else happens as it falls? It's going to speed up. And what type of energy does that generate? It generates kinetic energy. And as a matter of fact, there's an interesting relationship that happens here. So we know that at the top, the gravitational potential energy is 1,962 joules. During the fall, the gravitational potential energy decreases, and the kinetic energy increases. I guess it's not super clear yet, but what has happened here is the gravitational potential energy has turned into kinetic energy, to the point where at the bottom, all of the energy is now kinetic energy, 1,962 joules of it. We could even write a little equation that says something like this. PEG at the top is equal to the kinetic energy at the bottom. And since we know the gravitational potential energy at the top is 1,962 joules, and we know the kinetic energy equation is 1/2 mv squared, and we know the mass of the object, we could solve for the speed. Mass was 50 kilograms. So we do 1/2 of 50 is 25, 1,962 divided by 25, and we take the square root. We see that the speed of the object right before it hits the ground is 8.86 meters per second squared. So this is a situation in which we would say, since the energy at the top is equal to the energy at the bottom, just changed forms, energy is conserved. What happened was all of the initial gravitational potential energy, PEG, was converted to kinetic energy. I'll put a final in there because it was at the end. Now, you might be looking at this and saying, okay, well, how do we know that that's actually the speed? Is there any other way we could verify the speed? It turns out there is. Think back to kinematics. We're just dropping something. It's in free fall. I know the initial speed is 0 because it's falling from rest. I know the height that it's at, and if it's in free fall, I know the acceleration. So I could write something like this and see if I get the same speed. Vf squared equals vi squared plus 2ad. Initial speed is 0, it fell from rest. Vf squared equals 2 times 9.81 meters per second squared times the height, or the distance it fell of 4 meters. 2 times 9.81 times 4, 78.48. Take the square root to find Vf. Yeah, I get the exact same thing, which is interesting because imagine if you had got something different. That wouldn't be possible. Okay? If you got something different, that would say that one of these methods has to be wrong. So it's good that we got the same thing. Okay? So there we go. A lot of people will still use kinematics here. I just wanted to point out that you could use energy to find that final speed. All right? So we did a little bit with gravitational potential energy. The final type of energy we're going to talk about in this video is called potential energy stored or in a spring. So you might also hear me refer to it as elastic potential energy. Okay? So this is the energy associated with stretching or compressing a spring. Remember, a spring is anything that stretches or compresses or otherwise deforms its shape. So I've got a rubber band here. If I stretch out the rubber band, I'm storing elastic potential energy. It takes a force for me to do that, but I'm storing energy in here. Can't really compress a rubber band, but anything else that you can compress, like a spring, that is also something that can have this elastic potential energy. I'm going to put that in parentheses. Elastic potential energy. So how does an object gain spring potential energy? A force stretches or compresses a spring by some amount. I'm going to show you the equation, the derivation for this. This one's a little funky, but just follow along. And again, I'm not expecting you to memorize these derivations. They're there if you're interested, but I just want to show you that these equations don't just appear out of magic. Also, I'm throwing a lot of equations at you, okay? The equation for kinetic energy, the equation for gravitational potential energy, the equation for spring potential energy or elastic potential energy. You might be saying, why do we need all these equations? The answer is, you got to wait a little bit. You got to trust me. We use them because they're useful. We can solve problems that we wouldn't otherwise be able to solve by using these equations. So we're going to see it real soon. You got to trust me for a while because we're not quite there yet. Okay, so the equation. Just like the others, we're going to figure out how much work is done when, let's say, a spring like this rubber band, is stretched. Okay, so the work being done would be equal to an applied force times the displacement times cosine of theta. But once again, what applied force are we talking about? What displacement? Let's go back a little bit. Let's imagine that you have some object that's attached to a spring. Okay, so in this case, the rubber band. So you pull on the object, which also means that the spring or rubber band is going to stretch out and it's going to pull back in the opposite direction. So let's say that you have an object here. Here's your axis. Let's say that your applied force, you pull it to the right. That means that the object which is attached to the spring is going to try and pull it backwards. So that's Fs. The net force equation here would look like this. F net in the x direction equals Fa minus Fs equals max. And let's say you're just holding it there. So it's at rest. The velocity is not changing as well, so there's no acceleration. So that's 0. So you have your applied force equals the spring force. And as we remember, the equation for spring force is Fs equals Kx. So in this case, the applied force is equal to Kx. But there's an issue here. There's an issue because that implies that x, as you pull the object farther, that's going to make the spring stretch more. So as you exert a force over a greater displacement, that's going to make x change. D and x are kind of the same thing. Okay? D is the displacement that the force is exerted over. X is how far the spring stretches. Matter of fact, they are exactly the same thing. So as D increases, x increases by the same amount, which means Fa increases. And if Fa is increasing here, well, what are we supposed to plug in there? There's a sort of tricky way around it. Since the applied force is changing as x, I'm going to put a little line here, or in other words, D changes, here's what we're going to do. We're going to take the average value of the applied force during the course of the stretching. So let's say the spring is not stretched here, and we pull it out to here. So it's not stretched, no applied force, no spring force right here. Now there is an applied force because I got to hold this spring, this rubber band taut. Okay? What's the average force? If it goes from 0 to some amount, well, the average force would be whatever the average of 0 and that amount is, whatever that number is. So maybe something like right in the middle. Matter of fact, it should be right in the middle. So let's say if it's 0 here and 50 out here, well, the average force over that displacement would be 25 newtons. So we're going to say that the average applied force, remember that's a symbol for average, is half of the applied force when the spring is fully stretched to a distance, or to its length of, or its amount of x. In other words, if Fa is half, oh, excuse me, I forgot the Fa here. If the average force is half of the original when it's fully stretched to x, then we're going to plug in the average force. Wait a second, give me 1 second. Oh, okay. So if Fa is equal to Kx, then that means that the average force must be equal to 1/2 of the applied force, which is 1/2 of K times x. And again, remember, x and d are the same thing. D is the displacement as you do work. Okay, so if you pull the object, you're pulling it over some displacement. That's also stretching it the same amount. So you're stretching it a distance d. You're moving the object a distance d. You're also stretching the spring by a distance d, which we happen to call x. So what I'm going to do now is I'm going to plug in this applied force, this average applied force here, 1/2 kx. We just got done saying that d and x are the same thing, so I have 1/2 kx times x. And I can see that Fa and d are in the same direction, so it'll end up being cosine of 0, which is 1. And a better way for me to write this would be 1/2 kx squared. Now, okay, that's how much work was done. If there was no initial energy in the spring, then that means that the work done by the applied force went into changing the elastic potential energy. That's a symbol for elastic potential energy, PES. The work done equals PESF minus PESI. No initial stored energy. So therefore, the equation for elastic potential energy just happens to be how much work was done. In other words, PES equals 1/2 kx squared. And again, that is found right here on the reference tables. PES equals 1/2 kx squared. Don't get that confused with the spring force, okay? Spring force is K times X. A force is a push or a pull. Elastic potential energy, or spring potential energy, is 1/2 kx squared. That's a measure of how much energy is stored. And energy is really the ability of a system to either move or possibly move in the future. We'll talk more about what it really means later on. So we get down here. This is really the important part of this equation. The elastic potential energy is 1/2 kx squared. Okay. Two real quick examples. A water balloon launcher has a spring constant of 40 newtons per meter. Remember, spring constant is how stretchy a spring is. It is stretched 1.3 meters back and loaded with a 0.8 kilogram water balloon. How much potential energy is stored in the spring? This is pretty easy. Elastic potential energy is equal to 1/2 kx squared. The spring constant is 40 newtons per meter. X, the amount that it stretches, is 1.3 meters. Remember to square that. The amount of energy stored, 1.3 squared times 40 times 1/2, is 33.8 joules. If all of the potential energy in the spring is transferred to kinetic energy during the launch, what is the speed of the water balloon when it gets launched? This is another one of those conservation questions like we had above. This is going to be the main focus of our energy unit in about a week or so. So what we're saying is the initial elastic potential energy is equal to the final kinetic energy of the water balloon. The energy is initially stored in the spring. So imagine that spring getting energy stored in it by getting stretched out, and then at the last, and then when it's ready to release, the spring it goes back to its normal length, but all that energy's got to go somewhere. And it propels the water balloon forward, gives it kinetic energy. We know the elastic potential energy of the spring initially is 33.8 joules. We know kinetic energy is 1/2 mv squared. So this ends up being 33.8 equals 1/2. Water balloon is 0.8 kilograms. And we can solve for V. 33.8. Let's see, divided by 0.4, because 1/2 times 0.8 is 0.4. And then we take the square root, and we see that the water balloon gets launched with a speed of 9.19 meters per second. Okay? Expect more of those types of problems coming up, but ultimately what I wanted you to get from this video is a little bit of sense of how to work with gravitational potential energy and the idea that energy can also be stored in something like a spring. That's it for this video. I'll be back with some more on the energy unit in a little bit. Talk to you later. Bye.